Good morning, students. Today we will discuss about the first order low pass filter. So in the last class we have seen the first order low pass filter, but as there is a lot of disturbance in the last class in the voice, so I would like to revise this particular topic one more time. Okay. So in the first order low pass filter, the this is a circuit for the first order low pass filter. So in this circuit, the RNC component, that is this particular RNC component is acting as a low pass filter, and these two elements are acting as a feedback elements. These two elements are acting as a feedback elements, and this one is acting as a load. Okay. So across the load resistor, we are taking the output voltage. We are taking the output voltage across the load resistance. Okay. Then now R1 and RF are both are acting as a feedback elements. Both are acting as a feedback elements. Okay. Now this particular op amp, whatever the op amp we are having, this particular op amp is configured under the non-inverting terminal. As all of you know that the negative terminal is called as the inverting terminal, positive terminal is called as a non-inverting terminal of the op amp. Okay. So if you are connecting your input voltage to the non-inverting terminal of the op amp, then I can say that the op amp is configured under the non-inverting mode. Okay. So if you are applying the input voltage to the inverting terminal, there is a negative terminal of the op amp, then it is called as a inverting configuration. It is called as a inverting configuration, means op amp is configured under the inverting mode. Okay. So this is what we are having. Okay, now means we have taken the RC filter, which is the passive filter actually, which is a passive filter. But this passive filter will become the active filter by using the op amp, by using at least one active element. I told you that we can bring the passive network into the active network by using at least one active element. So here I am using the op amp as a active element. That's why this filter is called as a active low pass filter. Why we are getting the name first order, I'll let you know as we move on. Okay. So this is a circuit diagram. Okay. So now what I would like to do is I would like to calculate the output voltage for this particular circuit diagram. In order to calculate the output voltage, as I told you that this op amp is configured under the non-inverting mode. You are supposed to calculate how much voltage we are applying at the input of the non-inverting terminal of the op amp. I am assuming the voltage which is there at the non-inverting terminal of the op amp as a V1 voltage. I am assuming that V1 is the input voltage applied at the non-inverting terminal of the op amp. Okay. Now this V1 voltage is nothing but it is a voltage drop across the capacitor C. Means in order to know how much voltage we are applying at the non-inverting terminal of the op amp, first we should calculate the voltage drop across the capacitor. So here, in order to realize the concept more clearly, what I am doing is we are having the separate grounds, separate ground for the capacitor and separate ground for the VIN. Instead of that, I can take one common connection. I assume that we have the common ground. Okay, we have the common ground. So if you see this one, as per the basic circuit analysis, this one is acting as a one loop. In a particular loop, when you would like to calculate the voltage drop across one element like a capacitor, you can apply the voltage division rule to that particular loop. Means by applying the voltage division rule, you can calculate the voltage drop across any element in that particular loop. The voltage division rule says that across whom you would like to calculate the voltage drop, that impedance, element impedance by the total impedance in that particular circuit, that is the total impedance in that particular loop into the input voltage which is there, or the voltage which is there in that particular loop. The input voltage which is applied to that particular loop. That is what the voltage division rule. So as we know that the impedance of the capacitor is nothing but the ZC, impedance of the resistor is nothing but the ZR, and the voltage which is applied to this particular loop is how much? Vin. Voltage which is applied to this particular loop is nothing but the Vin. So based on this, the formula for the voltage drop across the capacitor is like this. So it is a impedance by the impedance of the capacitor by the total impedance that in that particular loop is nothing but the ZR plus ZC into the input voltage which is applied to that particular loop is a V. So this is the voltage division rule. Means by applying the voltage division rule, we would like to calculate the voltage drop across the capacitor. That voltage drop across the capacitor is nothing but it is the input voltage which is applied to the non-inverting terminal of the op amp. Input voltage which is applied to the non-inverting terminal of the op amp. Okay. Now here I am taking the ZC by ZR plus ZC into Vin. As we know that the ZC is nothing but the impedance of the capacitor, ZR is nothing but the impedance of the resistor. So go back to your previous video, that is a not live class, previous video. In the live class also we have seen that one. So ZC is nothing but the 1 by J omega C and ZR is nothing but the R only. So I am substituting those values and I am doing the simple mathematical calculations. After that, as we know that the W is nothing but the angular frequency, I would like to substitute the W value as a 2 pi f. The W is nothing but the angular frequency. We can write this one in terms of the linear frequency also. So that is nothing but the 2 pi f. So W is equals to the 2 pi f. I am just substituting that value. So finally, I got the V1 voltage, which is nothing but the voltage drop across the capacitor as a 1 by J 2 pi f RC plus 1 into Vin. So I am applying this is the input voltage, or this is the voltage drop across the capacitor, and also the same voltage is applied at the input of the non-inverting terminal of the op amp. Input of the non-inverting terminal of the op amp. Let's go to the next slide. So if you see this one, here what is our interest? Our interest is to calculate the output voltage of this particular circuit. But we know that the op amp is configured under the non-inverting mode. So we know the formula for calculating the output voltage of a non-inverting op amp. Non-inverting op amp is nothing but this is the formula. So means the output voltage at the the output voltage is nothing but in the non-inverting configuration mode. In the non-inverting configuration mode, the output voltage is nothing but 1 plus RF by, that is the feedback resistance by the input resistance into Vin. Here the Vin is nothing but the input voltage which is applied at the non-inverting terminal. Okay, non-inverting terminal. So that voltage is nothing but the V1. That voltage is nothing but the V1. So V0 equals to the 1 plus RF by R1 into V1. So we have seen the V1 now. V1 is nothing but the 1 by J2 pi f RC plus 1 into Vin. So I am simply substituting the V1 value over here. And I am doing some mathematical calculation, bringing this one to the left side. So V0 by Vin. Why I am bringing the this term to the left side means I would like to calculate the gain of this particular filter. Filter circuit. Okay. So what is the gain? Gain is nothing but output by input. The output may be in terms of the voltage. The output may be in terms of the current. The output may be in terms of the power also. Okay. So gain is nothing but output voltage by input voltage, or output current by input current, output power by input power. So the ratio of output by input of a particular circuit is giving the gain of that particular circuit. I'm just taking the V0 by Vn. So in the next step, what I'm doing is in order to avoid the complexity of the circuit, this particular equations, I'm assuming that AF is equals to the 1 plus RF by R1, which is called as a pass band gain. We will see the terms, or what is the name of each and every term as we move on. We will see that particular case. Okay. So the next is AF by J into 2 pi f RC plus 1. So in the next step, what I'm doing is I'm assuming that I'm just rewriting this denominator in terms of the 1 by 2 pi RC. I'm assuming that term as a FH. Actually, RC is nothing but what? RC is a time constant. Reciprocal of the RC is nothing but it is a frequency. Okay, RC is nothing but it is a time constant actually. So 1 by T, RC equals to the T means 1 by T is nothing but the frequency. So I'm assuming that as a FH frequency. Okay now. So in simplification, AF by J into F by FH plus 1. So here the FH is called as a high cutoff frequency of the low pass filter. We'll see the terms as we move on. Okay now. So now we are having the V0 by Vn equals to the AF by J of F by FH plus 1. I'm not interested to see the gain of the circuit in terms of the imaginary factor. So that's why what I'm doing is I'm just replacing this particular term, means I would like to get the information in the what is that gain format, means I'm not interested in the imaginary term. So that's why I'm applying the modulus to this particular circuit. When I'm applying the modulus to this particular equation, then I'm going to get the modulus of V naught by V in equals to the AF by, we know that A plus IB. The modulus of the A plus IB is nothing but the square root of A square plus B square. Okay, the square root of A square plus B square. So that's what we are getting, square root of 1 plus F by FH whole square. F by FH whole square. Okay. Next, we have calculated what ma? The gain of this particular circuit. V naught by V in. We calculate the gain of this particular circuit, which is nothing but the V naught by V in. Now, I would like to take the same formula and I would like to realize how exactly this means. Using this particular equation, I would like to comment that whether this particular circuit is acting as a low pass filter or not. Whether this particular circuit is acting as a low pass filter or not. Okay. So for that, what I'm going to do means I am going to change the input signal frequency, means I would like to take the input signal frequency, so on so thing, and how exactly the gain is changing. So I would like to concentrate on that factor. So before that, let us see what are the factors which we have used in this particular equation. Okay. So AF is called as a pass band gain. F is nothing but the input signal frequency over here, input signal frequency, and FH is nothing but the high cutoff frequency of the low pass filter. Okay. I will see whether this one is acting as a low pass filter or not. So after that, V naught by V in is nothing but V naught by V in is V naught by V in is nothing but, wait a minute, no. Someone trying to I'm doing the same thing now. Okay. Okay. So here AF is nothing but nothing is there. So I got the message from one of the student. Okay. So AF is nothing but it is a pass band gain. F is nothing but the input signal frequency. FH is nothing but the high cutoff frequency of the low pass filter. And V naught by V in is nothing but it is a gain of the low pass filter. Now we are interested to check it out whether this circuit is acting as a low pass filter or not. Okay, now whether this particular circuit is acting as a low pass filter or not. Further, to cross check this one, means whenever we are having circuit, remember ma, whenever we are having one circuit analysis using the mathematical equations, the final equation, understanding the final equation plays a major role. Okay, understanding the final equation, why we are getting that particular equation, understanding the final equation of that particular circuit plays a major role. If you analyze that particular final equation, then you got the complete information regarding that particular topic, as well as what is the circuit, what you are seeing. Okay, so here in order to analyze, what I'm doing is I'm just taking the this particular one, which is nothing but the gain of that particular that is we have the equation V naught by V in, so that is the gain of the equation na. This is the gain of the filter na. This is the gain of the filter, which is nothing but the modulus of V naught by V in equals to the AF by square root of 1 plus F by FH whole square. So now, in order to cross check this one, what we are assuming ma? We are assuming the input signal frequency. What exactly the low pass filter? So what you do is you just recollect the passive low pass filter. That is we have seen the ideal characteristics of the graphs, na? Ideal characteristics of the filters, na? Graphs, we have seen the graphs, right? I'll go back, wait a minute, I'll go back to that one. Yeah, what you do is just draw this particular one. So especially in this here we are having these graphs are related to the ideal filters. Okay, now means theoretically we are expecting that the low pass filter graph should be like this, high pass filter graph should be like this, band pass filter graph should be like this, band stop filter graph should be like this. Okay, now we assume like that. Okay, now it is not the assumption, actually it is a response of a particular filter, theoretical response. Okay, now we will see the practical scenario also. We will see the practical scenario also. Okay, if at all my practical circuit is giving the response like this, then I can say that it is a low pass filter. If at all my practical circuit is giving the response like this, the response means the gain of response between the what? The gain of the circuit as well as the input signal frequency. Okay, now. So if we are getting the response like this, I can say that my circuit is a high pass filter. If I am getting the what is that graph like this between the gain of the circuit and the input signal frequency, then I can say that it is a band pass filter. If I am getting like this, then it is called as a band stop filter or the band reject filter, band stop filter or the band reject filter. Okay, band stop or the band reject filter. Okay, so this is the ideal characteristics. These are indicating the ideal characteristics of our respective filters. Okay, so you just remember this, and I'll go to my explanation, continuation to the first order low pass filter. So we are up on the edge regarding this. Okay, so here in order to realize this concept, we are supposed to substitute the different values of the input signal frequency. Input signal frequency is nothing but f is called as an input signal frequency. So I would like to apply a different input signal frequencies in place of the f, and I would like to calculate how the gain of this particular equation is varying. Further, I'm taking the 3 points. In the first point, I'm assuming that the f is less than the cutoff frequency. That is, the input signal frequency is less than the cutoff frequency of the low pass filter. Then what could be the response? Okay, f by fh. Here I am assuming that f is less than the fh. So obviously this ratio, when the f is less than the fh, obviously this ratio is going to be a big value only, because the denominator factor, which is the fh, is here f is less than fh, right? So f is less than fh means here in this particular I'm substituting this assumption in this particular equation. When the f is less than the fh, obviously the denominator is greater than the numerator. That is the denominator is greater than the numerator. When we are having one ratio, and in that ratio if the denominator is greater than the numerator, so obviously we will get the fractional value. If you are squaring that particular fractional value, again it is going to become the very small value. Let us suppose the fraction value f by fh is a 0.1. Squaring of that one becomes a 0.01. Okay, now so 0.01 is very less than very less compared to the 1. Means 1, if you add the 1 to that particular 0.01, you will get the 1.01. So that is not going to affect much on the 1. So I can round it off this one, that particular 1.01 to the 1. 1.01 to the 1. Then the entire entire denominator becomes what? 1. Square root of 1 is nothing but the 1 only. Square root of 1 is nothing but the 1 only. Again I am repeating, if the input signal frequency is less than the cutoff frequency, that is the f is less than the fh, in this particular ratio, as the greater value is in the denominator, then this particular ratio gives the fractional value. Squaring of that one will give the very small value. If you are adding that small value to that 1, then that entire result becomes the approximately equals to the 1 only. So if you are squaring of that particular 1, square root of 1 is nothing but the 1. So obviously we are getting the AF by 1. AF by 1 is nothing but the AF only. Means when the input signal frequency is less than the cutoff frequency of this particular circuit, then the gain of that particular circuit is nothing but the AF only. Now I am taking the second condition. If the input signal frequency is equals to the cutoff frequency, if the input signal frequency is equals to the cutoff frequency, then the gain of system is nothing but f by fh, f equals to the fh. So obviously this ratio becomes a 1. So 1 means square root of 1 plus 1 is nothing but the 2. So it is going to be AF by root 2. AF by root 2 is nothing but 1 by root 2 is nothing but the 0.707 into AF. Okay, means the actual gain compared to the previous step, the AF is reduced by 1 by root 2 times. I am taking the third condition also. In the third condition, I am assuming that f is greater than the fh. Means the input signal frequency is greater than the high cutoff frequency. So when the input signal frequency is greater than the high cutoff frequency, in this particular means this assumption, again I am substituting in this particular equation. So when you are substituting f by fh, f is greater than the fh in this particular equation. F is greater than fh means this one is going to be the bigger value only, because the denominator is a small compared to the numerator. So if this one is a bigger value, squaring of that one becomes a some more high value. Okay, now some more high value. So if you are trying to add this value to the 1 is not going to affect this value much, because it is a bigger value. This term is a bigger value. When this term is bigger value, then I am assuming that square root of this entire term becomes this term only, because if you are adding the plus 1 to the bigger value, 1000 plus 1 is nothing but I can round it off that one to the 1000. Okay, now I can round it off that one to the 1000. Okay, so means this denominator is going to be very high value. This denominator becomes a high value. When we are having in this particular equation, when we are having the denominator which is more greater than the AF, then obviously this factor, the result of this particular ratio is less than the AF only. So means I am going to get the gain which is less than the AF compared to the previous values. Okay now. So we have the three conclusion points. If the F is input signal frequency is less than the cutoff frequency, we are getting the passband gain, constant passband gain. If the input signal frequency is increased and which is equals to the cutoff frequency, then the gain of this particular circuit is reduced by 0.707 AF. Okay, now means it is a 1 by root 2 times the AF. If the input signal frequency is further increased, which is greater than the high cutoff frequency, then obviously the gain of this particular circuit becomes a very small with respect to very small compared to the AF. So for this we have the graph. Means I would like to draw the graph. Because I would like to check it out whether this response is giving the low pass filter characteristics or not. In order to check it out that one, what I am doing is I am drawing the graph between the what is the gain of the circuit and the input signal frequency. So this is a graph. It is a gain of the circuit. And this is the input signal frequency. As we have seen that this is the origin. So I am assuming the origin is a 0. Origin is obviously 0. When this F is very small, in the least case, the F value is very small, we are getting the constant AF. So that is what we are having over here. I'll see the cutoff frequency also. I'm having the next slide. So if the F equals to the FH, F is equals to the FH, this is what we are having. Okay, now this is what we are having. Means this graph is representing the almost equals to the low cutoff frequency of our low pass filter. This graph is representing the ideal characteristics of our low pass filter. Okay, now we have seen the ideal characteristics graphs of our filters in the previous just few minutes back, like low pass filter, high pass filter, band pass filter, band stop filter. So this one is almost giving the low pass filter response only. So I can comment that this filter circuit is acting as a low pass filter. Here, as we have seen, AF is constant, means when the input signal frequency is less than the FH. This is almost constant. Okay, almost constant. And when the F equals to the FH, this factor is the AF factor. That is the passband gain is reduced by the 0.70 times. Okay, 0.70 times. And after F is greater than the FH, when we are having the third point now, F is greater than the FH. At that time, it is very less than the AF. Means it is almost very much less than the second term also. So that's why it is reduced like this. But ideal characteristics says that ideal characteristics are nothing but what? This one should be a sharp cut. We should have the sharp cut. But I told you that we are not going to get the sharp cut. This red mark is indicating the ideal characteristics. Okay now. Theoretical explanation means after F equals to the FH, we should not get any signal. At the output. But practically, we are getting some signal at the output. This is what means we are expecting the sharp cut, but this is what we are having. Okay. So this is after cutoff frequency also, we are getting some signal at the output. Okay, now we are getting some signal at the output of this particular circuit. Clear. So this is a practical explanation. This is a practical the practical response of the circuit. Ideal response is the red color one, but we are not getting that one. Ideal response should be the red color one, but we are not getting that one. In the practical case, we are having this one. Now, in order to improve the filter, means actually we are not interested to accept these frequency components, because we are interested to accept the frequency components from we are interested to accept the frequency component from here to here only. We are not interested in this part. We are not interested this part. In order to reduce this acceptance of the frequency signals after the cutoff frequency, in order to reduce that one, what I'll do is I'll increase the order of the system. Okay now. So what is the order is a question. So initially we started this class as a first order low pass filter. Initially we started this class as a first order low pass filter. So we are saying that this circuit is a first order low pass filter because the low pass filter circuit is constructed using what? R and C. How many R and C's are there? Only one R, one C is there. So as we are having only one combination, then it is called as a first order low pass filter. It is called as a first order low pass filter. Okay now. So this particular reduction means from here we are having the reduction. This particular reduction is called as a this particular reduction should be very sharp, but it is not sharp, and it's some frequency after the cutoff frequency also some frequencies are accepted by the low pass filter. But in order to reduce this particular acceptance, in order to avoid these many frequency components after the cutoff frequency, what I'll do is I'll try to increase the order of the system. When you increase the order of the system, then this one means this is the ideal characteristics. Then this one is going to be reduced. Oh, sorry, wait a minute. Yeah, this one we are expecting. This is a first order filter. So if you are increasing the order, then it is going to be a little sharper one. Means only less frequency components are going to be accepted, allowed by the low pass filter. Okay, now we are not going to get the ideal characteristics anywhere. Okay, but we can reduce that particular frequency components. How many number of frequency components are accepted by the filter after the cutoff frequency? We can reduce that number of frequency components by increasing the order of the system. By increasing the order of the system. So in short, okay, now in short, if you see this one, this is the response of the low pass filter. This is the response of the low pass filter. We have other way of explanation also. For example, you are having means I would like to know what is the cutoff frequency of a particular low pass filter. What is the cutoff frequency of a particular low pass filter? Assume that you are having the graph. You are having the graph in your hands. The graph representing the low pass filter response. Okay, now in that graph means using that particular graph, you would like to calculate the cutoff frequency of a particular filter. They have not given the cutoff frequency, means they have not mentioned that this is the cutoff frequency of your filter, but they have simply given the graph paper. Okay, now graph which is representing the low pass filter response. How to calculate the graph? How to calculate the what is that cutoff frequency of that particular filter is a question. When you have graph only and we don't have any values for the what is that? If you want to calculate the cutoff frequency FH, we have the formula, na? So we have the using this formula. Wait a minute. Using this formula, you can calculate the cutoff frequency. You can calculate the cutoff frequency of the circuit. Assume that there means they have not given the values. They have not given the R value. They have not given the C value, but they have given only the graph like this, and they are asking you to calculate the cutoff frequency of your filter. Cutoff frequency of your filter. How we can do that one is a question. How we can do that one is a question. Okay. So I'll come to that point. How we can do that, and I'll come to that point. Okay, just wait a minute. We have the first order low pass filter. So why we are calling this one as the first order low pass filter? Because the low pass filter is designed using a single resistor and a single capacitor. What is the drawback of the low pass filter? What is the drawback of the low pass filter? After the cutoff frequency, so many frequency components are accepted by the low pass filter. So many components are accepted by the so many frequency components are accepted by the low pass filter after the cutoff frequency. In order to reduce the accepting the more number of frequency components after the cutoff frequency, we are increasing the order of the system. We are increasing the order of the system. So before going to that, let me show you one important point. When you are going through the multiple textbooks, some of the textbook will explain like this, 0.70 like that. Okay, some of the textbooks will say that this format. Okay, but we raised one question. If we are having only the graph, and would like to calculate the cutoff frequency, the other way means how to calculate the high what is that cutoff frequency of the low pass filter when you have only the graph without R value and without the C value. What you can do is simple way of explanation. What you can do is calculate the AF value. In the graph you will come to know that what is the AF value. On the y-axis, you will come to know that what is the AF value. AF value is nothing but the gain. Okay, that is the maximum gain of that particular filter. Okay, that particular filter. So divide this one with the root 2 times. Okay, that is nothing but the 1 by root 2 times. Then you are getting the 0.707. So means at what point the gain is having the value 0.70 times the AF. At what point the gain is having the value 0.707 times the AF. From there, draw one perpendicular line. It is the other way of explanation to calculate the what is the cutoff frequency of your circuit. Take the 0.707 times the AF value. Take the 0.70 times the AF value. Draw one perpendicular line onto the graph. So this blue color is indicating the response of the low pass filter now onto the graph. At what point on this particular curve, at what point this perpendicular line is touching the curve. From there, again draw one perpendicular line onto the x-axis. X-axis is nothing but the frequency. At what point on the x-axis your perpendicular line drawn from this particular point onto the x-axis, at what point it is touching, that is going to become your cutoff frequency. Okay, now so means we are choosing the cutoff frequency of the filter practically. Theoretically, fh equals to 1 by 2 pi rc. Theoretically, fh equals to 1 by 2 pi rc. How we can identify the practical cutoff frequency is nothing but draw a perpendicular line from the y-axis onto the curve. From which point you are supposed to draw the perpendicular line onto the curve is a question. So that point is nothing but at what point the AF is reduced by 1 by root 2 times. At what point the AF is reduced by 1 by root 2 times, or at what point the AF value is 0.707 times. 0.707 times. From that point, draw one perpendicular line onto the curve, and from there you just draw onto the x-axis. Okay, now at what point the line is touching on the curve, from there you draw one perpendicular line onto the x-axis. Then you will get the practical cutoff frequency of your low pass filter. Means without having the R and C components values and having only the graph, we can easily calculate the cutoff frequency of your low pass filter. Or some of the textbooks says that at what point the gain is reduced by the 0.70 times of the filter. Means at one point the gain of the filter is reduced by 0.70 times. That point is the cutoff frequency of your low pass filter. Not only the low pass filter, for the high pass filter also. Means at what point the gain of the circuit reduced by 0.70 times. That point gives the cutoff frequency of your filter. We are seeing this values in terms of the what is it, normal decimal values, that is a fractional values like that. But some of the textbooks explain this one in terms of the decibel graph. Okay, in terms of the decibel. The other way of explanation is at what point the gain. So here V0 by Vn, I am assuming that V0 by Vn equals to the 1. The gain AF equals to the 1. Means this is the AF value. AF is equals to the how much? AF equals to the 1. At what point this AF value reduced by 3 decibels in terms of the decibels? At what point this AF value reduced by 3 decibels? That point is taken as a cutoff frequency. Okay, now. So this is the cutoff frequency of your low pass filter. Okay. So on this x-axis we are having the FH. This is the cutoff frequency of your low pass filter. Clear? Means the other way. One way of explanation is at what point the filter gain is reduced by 0.707 times. The other way in terms of the decibel is at what point the gain is reduced by 3 decibels of the original gain. That point is taken as a cutoff frequency. From there, if you draw the perpendicular line onto the x-axis, it will give the cutoff frequency. Okay. So means this is how we can calculate the cutoff frequency of your filter. So the same thing is there for the high pass filter. I will come to that particular high pass filter later. Okay. So now if you see this one, SEMA, we are having the 20 decibel now. Minus 20 is nothing but reduction now. Means how far. The decade means 10 times the input signal frequency actually. It is a 10f. I can simply say that it is a 10f. Okay. So reduction means this is the cutoff frequency now. After this cutoff frequency, we are not expecting any frequency components. So this solid line is indicating the ideal characteristics of the low pass filter. After this solid line, we are not expecting any frequency component. But unfortunately, in the practical case, we are getting the so many frequency components. So this particular first dot, whatever the dots we are having, so this is indicating the first order low pass filter response. If you are go through any textbook and they are trying to indicate the information in terms of the decibel, then this reduction means the gain after cutoff frequency, the gain of this particular circuit is reduced by 20 decibels for every 10 times the input signal frequency variation. For every 10 times the input signal frequency variation, the gain is reduced by 20 decibel. Okay, now if you see this one, again so many components are accepted by the low pass filter. In order to avoid accepting so many components after the cutoff frequency, I am going to increase the order of the filter. Increasing the order of the filter is nothing but constructing the second order low pass filter. Constructing the second order low pass filter is nothing but, in case of the in designing the low pass filter, we are using the two resistors and two capacitors. We are using the two resistors, two capacitors. They are connected in such a way that it is going to give the second order low pass filter. It is going to give the second order low pass filter. When you are constructing the second order low pass filter, at that time the response of the second order low pass filter becomes this one. We will see the second order low pass filter circuit diagram also. Don't worry about it. But as time is as there is a explanation on this particular graph, I would like to cover all the things. Okay, now so when you take the second order low pass filter, this is the second order low pass filter response. Now if you see this one, in the first order case it is accepting so many components, but if you are when you are increasing the order, then it is accepting a less number of frequency components after the cutoff frequency. A less number of frequency components after the cutoff frequency. Okay, so means the AF is, that is the whatever the gain we are having, that gain is reduced. This is the gain response. Now actually this is a gain response. This gain is reduced very fastly compared to the first order. As we are having the second order, so the reduction is in the 40 decibels per decade. Means for every 10 times the input signal frequency variation, the gain is reduced by 40 decibels. Now if you compare this one, compared to the 20 decibel, 40 decibel reduction is very fast. Means it is accepting only very less frequency components compared to the first order. No sir, I am not satisfied with this one. Then I am going to increase the order of the low pass filter. That is nothing but the third order of the low pass filter. You can't increase them further, means to fourth order, fifth order, like that. If you are keep on increasing the order of the filter, then the complexity of the filter will means the complexity of the, there is a more complexity in the circuit diagram, and at the same time, even though you are trying to increase your order of the system, you will never get the ideal characteristics, because the components are not giving what we are expecting because of their internal properties and the characteristics. They are not giving the ideal values. Okay, as they are not acting as the ideal elements, so obviously we are not going to get this sharp one, but we can reduce the number of frequency components which are accepted by the filter after the cutoff frequency by increasing the order. So we are increasing up to the third order. If you increase the third order, then the reduction is a little more faster. So this is what the third order response. So in this case, only few components are going to be accepted by the filter. Compared to the first order, second order, then only less number of frequency components are accepted after the cutoff frequency. This reduction is called as a 20 decibel. Okay, now so 20 decibel decade. Okay, clear. So here the decibel format, all those things. This explanation belongs to the what is that control system format, but we are not interested to concentrate on the how exactly the control system is accepting. With the help of the Bodo plots, we are supposed to explain this one, but as it is out of syllabus, I am not touching that point. Just remember that first order is nothing but the 20 decibel. Second order is nothing but the 2 into, that is the order into 20. Third order is nothing but the order into 20. So first order is first order means 1 into 20 is nothing but the 20 decibels per decade. Second order is the 2 into 20 is nothing but the 40 decibels decade. Third order is the 3 into 20 is nothing but the 60 decibels per decade. Okay, now just remember that one. Okay, now actually it plays a major role in the Bodo plots, but I am not concentrating on that. Okay, it is not required for you in that means that much explanation. If you want to realize this how exactly the reduction is mentioned, then you are supposed to consider on the what is the zeros and poles. Okay, now. So if you are concentrating on the zeros and poles, and you are supposed to focus on the Bodo plots also to realize how exactly this reduction is there. So it is out of scope of this video. So if you are interested to know about that one, you just concentrate on any control system textbook. For example, we are having the Nagurkani control system by Nagurkani. If you want, you can go through that particular textbook about the Bodo plots. If you know the Bodo plots, then in the Bodo plots only you will come across the zeros and poles concept. Okay. So this is what we are having. Okay, means if you are increasing the order of the filter, then almost we are going to get the ideal characteristics, but we will never get the ideal characteristics even if you are increasing the keep on increasing the order of the filter. Okay, now up to certain limit only we can increase the order, because if you are keep on increasing, it won't give the ideal characteristics. Rather than that, we will come across a complex circuit. Okay, now to avoid that confusion, we are just terminating with the third order only. Okay, so let us go for the second order filter. Let us go for the second order filter. Okay, second order filter. So as I told you that the first order filter is nothing but this is a first order filter. The low pass filter is the this RC only giving the filter filter response. R and C combination is giving the filter response. Now here we have only one R and only one C, so that's why it is called as the first order low pass filter. Here if you see this one, we are having the two RC, two resistors and two capacitors. They are connected in such a way that to give the second order low pass filter. Or I can simply say that these two combinations, this circuit is giving the this circuit is giving the low pass filter. What is the order of this particular filter? The order of the filter is nothing but it is a second order, because we are using the two resistors. We are using the two resistors with the two capacitors. Okay. Now the feedback element. Here the feedback element is having the it is a pot. Why we are supposed to have the extra resistors? For that we have a lot of explanation, beautiful explanation regarding the operation amplifier, because whenever you are using the operation amplifier, along with the required components, we are using the extra components. Why we are supposed to use the extra components means to nullify the offset values, all those things. We are having the lot of explanation, but if you want to enjoy the op-amp concept, better to go through the Ramakant Gaikwad textbooks, the initial pages of the Ramakant Gaikwad textbook. Then you can see why we are supposed to use the other resistors which are not part of our actual circuit. Okay, now so there is a beautiful explanation. You just go to that one. Okay, now you just go to the op-amp by Ramakant Gaikwad textbook. Okay, now so this one is giving the what is that second order filter. Okay, now so again it is a second order low pass filter, that too second order active low pass filter. If you do the simplification and all those things for this particular circuit, you will come across the final equations. Like this is a V0 by Vn. This is the gain of the second order filter, which is equals to the AF by square root of 1 plus F by FH, which is a cutoff frequency of the what is that low pass filter. FH is a high cutoff frequency, means the highest frequency which is accepted by the filter is called as a high cutoff frequency, and it is a power of 4. Previously in the first order we have the square, but here we are having the power 4. Okay, now cutoff frequency formula is FH. As we are having the two resistors and capacitors, the formula is FH equals to, which is the high cutoff frequency of the second order low pass filter, equals to the 1 by 2 pi times the square root of R2 R3 C2 C3. If you want what is that avoid the complexity, what you can do is you can take the means you simply use the two resistors only, but with the equal values, means R2 equals to the R3, C2 equals to C3. Then you can reduce this equation. You can reduce this equation like this. Okay, now FH equals to the, you can reduce this equation. You can reduce this equation as a equals to, I'm not writing the FH, equals to 1 by 2 pi. I think I don't have the symbol, pi symbol, so I'm simply writing the pi, 2 pi square root of, I have to take the draw. So as we are taking the equal values, square root of square root avoids. So yeah, simple one is when R2 equals to the R3, C2 equals to the C3, what will happen? It will become the what is that? R2 equals to the R3 equals to the R, C2 equals to C3 equals to the R, C. Then this one is becomes the R square, C square. So square means square root avoid. Then the high cutoff frequency of the second order low pass filter also becomes a just like the high cutoff frequency of the first order filter. But simple way is this is the actual equation for your second order low pass filter. This is the high cutoff frequency of the second order low pass filter. So in order to realize this one, how exactly we are getting the gain of this particular one, that is the output by the input voltage for the second order low pass filter. I'll send you some some photographs in the WhatsApp group. You just go through that one, how you are realizing this one. In order to realize this complex circuit, in order to realize this particular complex circuit, what you are supposed to means in order to calculate this particular circuit, as we are having the complexity at the input, we are supposed to reduce this particular complexity. Actually, as I told you that when you would like to calculate the V0 by V in, first we should calculate the V1 value. V1 value is nothing but the voltage dropped out as a capacitor. In order to realize this one, we are supposed to translate these terms into the frequency format by applying the Laplace transformation. Laplace transformation of the resistor is nothing but the R only, because R is not varying with respect, R value is not varying with respect to the frequency. So that's why it is a R only. If you are taking the capacitor, Laplace transformation of the Laplace transformation value for the capacitor is nothing but the 1 by CS or SC. 1 by CS or the SC. Okay, now. So further you are supposed to do more analysis. So as the complexity, as the video length is increasing, I'm not focusing that one. I'll send you the photographs for that. For that particular explanation. Okay. So second order low pass filter. In the second order what is the second order low pass filter? Using the 2 resistors and 2 capacitor and constructing the connection like this, it becomes the second order low pass filter. And this one is the cutoff frequency of the second order low pass filter. This is the gain of the second order low pass filter. I will clear so far. So why we are supposed to increase the order of the filter? Means to avoid the accepting more frequency components after the cutoff frequency. So this is what we are having. So here we are having this is the ideal characteristics, means a sharp cut is there after the cutoff frequency. We are not expecting any signal as per this particular graph. But when you come to the practical one, this solid line is indicating the graph now. So this one only indicating the graph now. So but the practical one is giving the dotted lines, means after the cutoff frequency also we are having some frequency components. We are accepting some frequency component. To avoid that one, we should increase the order of the system. Order of the filter. System is nothing but the filter. Okay. So that's why we are taking the second order filter. So as per the syllabus, we are simply stopping at the second order filter only. We are not going with the third order filter. If you want to go to the third order filter, then obviously you are supposed to go for taking one more RC combination and placing that one in the circuit. Then it is going to become the third order low pass filter. I hope you realize the concept. So I'm stopping over here about the low pass filter. I'll send you. I'll continue in the next video with the high pass filter. Okay, now with the high pass filter, I think time is exceeded. Time is exceeded. So what I'll do is I'll stop my explanation over here, and I'll make one more video on the high pass filter. Okay. If you are having any queries regarding this one, let me know that one. And whatever the the material which I sent you through the WhatsApp, that one is not giving the complete information. That is the theoretical points. Only the equations and the terms what we are calling, that information only is there. But we are supposed to add some theory points here or somewhere. Okay, here or somewhere. Okay, we'll see that one as we move on, because from the November onwards we are expecting that there are offline classes, means you are supposed to come to the college based on your interest only. I'm not sure what will happen in the November, so let us wait and see. Okay, so what you do is for a reference point of view, whatever the document I send you, just follow that one, put it that one on the notes. And for every topic, after every topic, better to leave some space in your notes. If you are writing the notes, better to leave some space, like one side of one complete page, because you are supposed to add here are somewhere some theory points should be added. So you can write the those points there. Okay, now just leave some space for after every topic. Okay, that's all for today's class. If you are having queries regarding this particular topic, let me know. What I'll do is the remaining sessions also I'll go with the video classes only. Because I'm not satisfied with the last class explanation, means the live class, I'm not satisfied with that one. So that's why I'm going with the video classes only. What is going to happen in the future, we'll see that one, the consequences, because we have some negative feedbacks on this. So even though we have the negative feedback, I'll go with the student comfortable zone only. So that's why I'm going with the recorded class. Okay, now if you are having any queries regarding this particular topic, then let me know in the group or in the comment section. Okay.